Hi everyone, my name is Davor Carrick. I'm a student over at University of Ottawa, studying under Dr. Jeff Lundeen, and I will be showing you high-dimensional multi-path quantum state estimation. So whenever we want to transmit information from one party to another, we have to choose a medium with which to encode our information. For photons, polarization is a very popular choice. So here we encode our information on the possible polarization states, so horizontal or vertical, that the photon may be in. And in particular, we can encode it into the superposition of these. So in the possibility that it is both H and V. One good part of polarization is that it's very easy to use. We have a very robust background on how to use polarization for many different things. But it is quite limited in dimension. Of course, there's only two polarization states that it can be in. It can be in a superposition of these, but there's still only two. The other limitation is one of future proofing, as we tend to move towards on-chip photonic devices where polarization is not really well maintained. So this and especially in free space and even in satellite communication, where it's really hard to determine what the polarization is between the two parties. One popular alternative to polarization is to use the different possible paths that a photon can be in. So here, instead of encoding our information in the different polarizations, the photon might be in paths 1, 2, 3, and so on, and we simply encode the information on whether or not the photon is in one particular path. One good part about this is that it's really high dimensional, and it's really easy to add dimensions. You just have to add more paths. However, a difficulty to this is that it is hard to measure these states. And that is really what I want to focus on today, is how do we measure such a state. In particular, consider such as this image, which is universal multiport interferometer that outputs its result as many different paths. How would one reconstruct the total output state of all those paths? So traditionally, reconstruction methods scale poorly in both a theoretical, so generally as the dimensions squared, but also in an experimental sense. So one naive way to reconstruct these would be just to interfere them pairwise. But of course, not only is that very time consuming for a large dimension, it's also practically very difficult to do. So as a means to do this estimation, I want to present it to you in terms of an example. So suppose that we want to reconstruct the state of these 6 propagating beams. So these beams are labeled 1, 2, 3, 4, 5, and 6 as shown in the figure here. And the state is represented by something called a density matrix. So if you've never seen a density matrix, you can think of it as an extension of the usual quantum states that we work with. So here the diagonals, A11 through A66, represent the different populations of each path, so you could think of these as the intensities of each path. The off diagonals here, and really the thing that we'll be concerned with, are, so such as A16 in this example, represent essentially a measure of the amount of superposition going on between each paths. So this is in essence what you can think of as what makes the system quantum to begin with. So a simpler example before we do the six paths. Suppose that we want to reconstruct this state of 2 parallel propagating beams. So now our density matrix is just 2 by 2. We have the diagonals and we have the off diagonals. So if the off diagonals are a measure of the amount of superposition, and superposition is what makes interference possible, can we use interference to recalculate the coherence values? So hopefully you've seen something like this before in either your optics or E&M class, where you can calculate what the interference between two interfering waves would be. So of course this form is usually of some constant, so 1, that is modulated by a cosine function. And the depth of modulation, or the visibility of the interference, we can see is directly proportional to, or is essentially equal to, the magnitude of the coherence value, in this case A1, 2. We also see that the phase of the interference pattern in the cosine is equal to the phase of A1, 2. So all the information is encoded into the interference pattern, we just need a way to get it out. Unfortunately, visibility can be kind of tricky to work with. It's not too bad if you have in the image before, you just take the maximum and the minimum of the interference patterns, and that will give you the visibility. However, this is a lot harder to do if you have multiple interfering beams. And of course, phase always requires a reference. So our solution is to this, as of course we're dealing with oscillating signals, and anytime you have an oscillating signal, the first thing that you do is Fourier transform it. So the Fourier transform of this interference pattern that we had before is of course given by delta functions. And we see that the prefactors multiplying the delta functions are our coherence values. Now, of course, the Fourier transform is a complex valued function, so not only do we have the magnitude of the coherence value, we have also the phase of the coherence value, all encoded into the real and imaginary part of the Fourier transform. Very importantly, I'd like to point out the frequency at which these peaks will show up is directly proportional to the spacing between the paths. So here delta 1, 2 is the spacings between our paths 1 and 2. And this will be important in a moment. So the reconstruction so far appears fairly easy. Step 1, you interfere the paths. This part is really easy, at least optically, because you can do it all with just a lens. So of course a lens will interfere the two paths, and you just image it onto a CCD camera, and then in step 2, in post-analysis, you just Fourier transform the interference pattern to recover your coherence values. However, when we go back to our original example, we have a bit of a problem. That is one of equal spacings, as we like to call it. So of course, I mentioned already that when you Fourier transform a signal, the signal will appear at a frequency determined by the spacing between the two paths. So if you have multiple repeated paths, such as in this case between 1 and 6 and 2 and 5, and of course 1, 2, and 6, 5, then all of those signals will overlap, obscuring the result that you want. Moreover, even when you go to interfere them, you could have this situation where the coherences have the exact same magnitude but the opposite phase. If you use a normal lens, so a two-dimensional lens, the coherences will actually completely destructively cancel out together, and you will not be able to see them. So in this case, you cannot tell between coherent but out of phase or lack of coherence. So of course, this is a big problem. So our solution is, what if we spatially separate the interferences that are giving us problems? So of course, one way you could spatially separate them is by using a beam block, but the other way, and hopefully you agree a much more intuitive way, is to use a cylindrical lens. So of course, a cylindrical lens acts as a regular lens but only in one dimension, and leaves everything else alone in the other direction. So here we can rotate the axis of the cylindrical lens to hit pairwise each of the interference patterns. to get something like this. And you can see all of the interference patterns, and you can see that for theta equals 0, we have our 3-slit interference, which we will be able to resolve. I wanted to make a tiny point here. Notice that even though all of the other paths here have been stretched out, their total intensities have not changed. They've just been redistributed. Because of this, we can also use these images to reconstruct the diagonals. This is nice because you don't have to make a separate setup to reconstruct the diagonals. All of the information is in the images, so you don't have to lose any light to reconstruct them. So here's the experimental setup. Now that we've introduced the theory behind it, let's try and test it out. So the top part here in A, I won't discuss too much. You can think of it as a black box that produces those six path states. The way that we do it is just by using some calcite beam displacers, and we have some half wave plates and quarter wave plates to change the phase between the paths. So if you think of this top part as just generating our 6 paths, really the experimental setup is just this bottom part. So in reality, all it is a rotating cylindrical lens followed by a CMOS camera. So we image the interference patterns. So here you can see again the 3-slit interference. We take the Fourier transform in post-analysis, and we get our Fourier transform spectrum. And because we know the spacing between each of the paths involved, we can uniquely identify each one of these Fourier transform peaks with one of the coherence values. So finally, some results. Here I am reconstructing the 6-dimensional state given by our paths. What I'm plotting here is the upper triangular coherence elements. So I'm not plotting the diagonals and I'm not plotting the conjugates. We have a quarter wave plate in the setup that rotates to vary the elements, but of course the possible values that we can generate are limited. Nevertheless, you can see that the reconstructed elements agree quite well with the theoretical predictions, which are given by the solid lines. One can also calculate a measure called the purity, which tells you how close two density matrices are. So in this case, we're comparing our theoretical density matrix with the experimentally calculated density matrix, and a fidelity of 1 tells you that they are the exact same. Here we get a fidelity of 0.985, which is fairly decent. However, I would like to note that in this estimation, no likelihood methods have been employed. So no algorithms have been employed to do parameter estimation, so you can think of this as just the raw data in some sense. We can also add in some optical elements that will decohere the state, and this manifests as a reduction in something called the state purity, which we can calculate and we can plot versus the theoretical value. And you see here that it agrees again quite well. So just some final points that I wanted to leave on. The number of settings that you need, so for the angle of the cylindrical lens, depends on the geometrical arrangement of the paths. So of course, as one example, if you have n paths all along a line, then you can reconstruct all the coherence elements in just one experimental setting. This example is also kind of particularly useful because you can use this setting for real-time analysis of some perhaps time-dependent coherence values, because you don't have to hold the system while you scan the different elements. Here you can actually analyze the coherence values as a function of time, which is something that you couldn't normally do in general setups. Another point is that you can also reconstruct bipartite states just as easily. So one common bipartite state is path polarization entangled photons. All you need to do is simply re-encode the polarization into different path states. So you can just use one more walk-off crystal to do this. And then the reconstruction method is the exact same as described before. And my final point here is that, at least to me, this is somewhat conceptually cool. In order to reconstruct the state, what we're doing is we're going into momentum space, or Fourier transforming. This is because lens, essentially from Gaussian optics, acts as an analog Fourier transform computer. So if a normal lens is a 2D Fourier transform, then a cylindrical lens is a 1D Fourier transform. So what we're doing is we're going into the Fourier transform space in one dimension of our Hilbert space, and we reconstruct our state simply by rotating which direction that Fourier transform is occurring in. Of course, reconstruction methods always require something to be scanning, and this is what is scanning in our case, and I think it's kind of conceptually cool, at least. With that, I'd like to thank you for listening.